Welcome to SimScale training on data analysis. My name is Paweł Sosnowski and I will have the pleasure of being your host today. Let's jump in and begin. We'll go to the offline post-processing using ParaView, which also gives us additional tools and more capabilities to play with. I will be working with the ParaView version 4.3.1 since it allows my computer to go for. I don't have a bad laptop or bad computer. At the same time, you need a pretty good graphic card to handle the newest version 5.0.0. So most likely you will need to install some good graphics card that can handle big 3D imaging. On the other hand, the version that I'm talking about is pretty good itself and allows great image processing. A first look at the graphical user interface. The main toolbar that contains information, obviously with the files, views, filters, and so on. Then we have the pipeline browser, similar to what we've seen in the online post-processor. Speaking of which, before I proceed, we have a question. With the online post-processor, can you probe a model to find the stress at a specific point? Yes, you can do that. There is a particular filter called probe location or plot over line. With that, you can visualize the results at particular points or along the probe line that is being posted there. But getting back to the ParaView graphic interface, I'll also go to show this probing tool in the offline post-processor. The next thing are the properties or information about the filter that we are playing with. Further, the time controls, things that we already know, the camera controls, axis centers, all of them were already positioned inside the online post-processor. Then the renderer view, which allows us to have multiple screens open with multiple results viewed. And it's time to go offline and see the results. There we go. First thing that I personally like to do before performing any kind of visualization is to change this nasty background. In order to do that, we go to the Properties, open the Advanced Properties with this little gear tool, scroll to the very bottom and choose the background settings. Here I can choose a gradient control, and by choosing the second color to be white, I get a nice screen representation that will make my visualizations look much more interesting. Even though we're trying to make a good representation of the data and we're focusing mostly on the quality of the results, some aesthetics brings a good understanding and allows us to appreciate the results a little more. So we can play with it. First thing that I would like to show you are the CFD results. Obviously the same filters or same approaches will apply for stress analysis and so on. Let's take a look at an example of result for a transient simulation. The results will consist of multiple data elements. In a very similar fashion, we'll have it for stress analysis. We'll have particular data elements that represent the time steps and saved fields. So from 1 to 2.6. Then there are some folders that contain information about the mesh and the system settings. And finally, the empty file, 0 bytes, called case.foam. We're using OpenFOAM as the CFD tool. So this particular file will define that the folder with the data contains a structure resembling OpenFOAM data. For structural analysis, we will have a VTK setups. And I will simply load this into ParaView. first thing to decide is what kind of results or what kind of data do I want to visualize. We'll go with the internal mesh and we'll take both fields. Very often you would like to remove one of the fields in order to get more memory efficient. I'll just do that. We'll remove the pressure and keep with velocity. After I click apply, the data is visualized on the screen. And we're ready to start playing with the filters. We have the same setup as clips, slices on the default sets, and more. Lots and lots of more filters. Most of the time you will be using 3 to 7 of them, but it's good to know that there is a big library of possibilities available under your fingertips to play with. Let's try to make the first analysis. We'll just go with a case.foam. We'll apply our first slice. There we go. We can go to the properties, scroll up and hide the plane so it doesn't obscure the view, and color it with velocity data. Or we can jump to the last time step, choose the rescaling data sets to represent what we have here. We'll just keep with the with the cell data to have the understanding of the mesh quality for this particular geometry. Now this is a transient simulation, so I can start playing around with the time and see how did it develop in transient space. For this particular simulation, I decided to increase the inlet velocity from a very slow, from 0 to up to, I believe this was 2 meters per second at the inlet. Let's reset the view, select it at front. We can also move the scale so that it doesn't block too much. And now I would like to create an animation that later will be used to demonstrate the results. We'll start with saving an animation, choosing the number of frames per second. We will use 10 frames per second just as an example, choosing the resolution and saving the animation. I'll just go to the desktop and save AAA. There will be some warnings appearing that, well, we need to crop the size a little bit. We just go with it. And in a second, the simulation will start to be processed and visualized in the format that we decided to have it. Let's give it some time. And now, if I just jump to my desktop, if I manage to do that, I have the animation ready and we can enjoy the results that we've just created. What if that was all? It would be all in vain. Again, we would like to have the possibility of representing the rest of the data, or let's say having some more sophisticated views. What we can do is, for example, show the case and give it a property of, and give it some opacity. You just scroll down in the advanced properties and find the styling menu, choosing the opacity. Maybe 0.4 is a little too small. We'll give it 0.6. There we go, a ghost body that contains our clip. We could also try to add extra features like extra elements. Nothing stops us from opening the same filters once more. We can load the data source for the second time and at the moment switch off the fields, switch off the internal mesh, and choose the particular faces that we would like to have as a full solid object. And one would ask, how do I know which faces are interesting? Right now we have some faces on the top, and it would not look very good if we were playing around with all of them just by try and error. That's where SimScale comes to help. We can go back to our geometry, go to the simulation designer and choose the simulation that we used for this particular setup. See the topological entity sets. We selected earlier at SimScale the faces. So I will just hide all the walls and show the valve. We will select the valve and see the face numbers in the scene viewer that are representing the position of the valve itself. So it will be 33, 39, 40, and quite a lot, and everything from 81 below. So I'll jump back to the post-processor and start choosing. And now I forgot. 33, 39, 40, and everything from 80 to the bottom. After I apply this, we have the solid element representing the valve present without opacity as a second source of data. Obviously, we would not like to apply filters to this one, so I'll just rename it and give it, just clicking on it, give a name, for example, shell, do not touch. Now we can apply stream tracers to the main data where we loaded the internal field. We'll be filtering and simplifying this representation. So I'll just hide the slice. We have a very nice representation. We'll go and show the velocity field once more and a very nice representation of it. We can again save screenshots if we so desire. And later use them for visualization of other elements. The next thing that can be of interest is choosing the second renderer to have multiple images shown at the same time. With the second window open, I can choose the renderer view and decide which data elements should be visible. I'll choose the stream tracers and the streamlines. Further, once more, I will add the opacity factor to the whole body and choose a color for the stream tracer. We can set up the position using one of the default axes and this way have another way of visualizing the whole thing. Again, another screenshot. Very nice. Further filters that are available go around with creating contours, thresholds, stream tracers, warping by vectors, which is very interesting for structural analysis that will bend the structure with the displacement that was applied, having the access to calculators, once more the same element that we used previously in order to make manipulations of the data that is available for us. But one more thing that I would like to show you is a very nice visualization technique used for static analysis, steady state analysis of fluid flows. We'll go and find the data set itself. This time we'll just have several elements from 0 to 1500, which will result in a steady state simulation. Nothing interesting, we would say. Let's just delete all these elements, reset the viewer, and we'll load case.fo. Apply it. There we have it. If we scroll to the very end, we'll have the final state of the simulation with the velocity field. We'll make a slice. I'll say I will not be able to make any animation out of it. But not necessarily. We have the possibility of playing with an offline visualization tool. That's why we'll start with choosing the view and showing the animation view tool. This thing allows us to control multiple variables that are present in the filters. For example, we could choose to change the origin of the slice. Choose the X origin, that is the 0 component, add it, and now we need to change the mode of the animation creation from a snapping to time steps, which makes no sense for a steady-state simulation, to a sequence. And this sequence will start at 0 and will end at 20. We'll have 20 frames created this way. We'll be sequencing the data. The second thing is to check what kind of timekeeper are we dealing with. By default, it will be using the animation time that is snapped to the results that we have. We'll choose a constant time source for the whole analysis, whole animation, and we'll keep it at 1500, so the last result. Finally, we'll choose the behavior of the slice. We will simply ramp it from 0, from the smallest value to the maximum value at X, having 20 steps. This is ready. Let's hide the plane, scroll a little bit out, have the pressure field done, and start saving an animation. We'll keep 5 frames per second so that the animation is a little longer, and maybe, yeah, it can be a little longer. We'll save it in AVI format. There are multiple formats that you can play with. There's the free open source OGV, AVI, or you can have each of the results as separate images in JPG, TIFF, or PNG format. But I'll go with AVI. There we go. The slice will start moving and changing its origin at from the very beginning. So now let's take a look at the result, which makes a static simulation a little more dynamic. This also helps you make the visualization of a whole field and allow for full analysis of each element of the result that is present in the whole domain itself. Most of the time we are seeing just the streamlines or a single slice. With an animation, a dynamic animation like this, we can access each and every point of the domain. But that's not all what we can do. Let's start playing a little more. I'll just delete the slice, choose the coloring to be the solid color, and we'll give some opacity. So there it is. To the body. Further, we'll put the stream tracer as a point source, but this time I will position it close to the inlet. somewhere here, and apply. We'll have the multiple streamlines created and choose the coloring by velocity. For example, let's set up the view and hide the little point so it doesn't obscure what we are trying to show. So we'll hide the point. And now we'll first of all again go to create a sequence, check if our timekeeper is at constant time, and this time with the stream tracer as the source of the change in animation, we'll choose the maximum streamline length and add it to the controls. We'll ramp the value from 0 to 0.33, which is the, I think, maximum value for this particular run, and save the animation. Once more, let's give it 5 frames per second and create the third animation. Once more, we were able to create a dynamic simulation of a steady state flow, which brings some life to our results and allows to visualize it to our colleagues and co-workers in a nice way. But these are colorful images, and some would say we want hard evidence, hard data, something more that is not just colorful pictures. We'll just hide the streamlines and start using different filters, such as probe location. I'll just try to look at it. This particular filter will find and calculate, will find the value of the field, of all the fields located at this particular probe point. I'll just apply this. Obviously, this representation is not the correct one to show it. For this, we'll open the second viewer, second window, and choose the spreadsheet view, which will present all the elements that are stored in this particular location in space. First, we have the point data, that is the interpolated values at this place, using the values stored at the mesh intersections. And the cell data that at this particular situation are not calculated or are not probed. So we can see what is the value of, what is the position of the point, the 3 components, what is the velocity, the value of epsilon, k, nu t, all the parameters that are stored there. This data can be later saved as a saved data, as a CSV file, as an example. Let's go to a desktop, give it a name, and later it can be accessed and viewed for further processing. But that's not all. This is just a single point. We could add other filters, such as plot over line. Not only do we calculate the values at particular locations, but we'll have the full analysis of the change of the field with certain 100 points positioned along this line. Let's just move it a smidge lower. There we go. After applying it, another viewer will appear. This time it is the plot viewer that shows all the fields that are present in this particular simulation. We can hide some of them just so they do not obscure the view. So we'll just hide epsilon, we'll hide k, we'll just keep, for example, velocity, and we just need to use the rescale reset view in order to see the full thing. In this particular situation, we notice that there are these little jumps or lack of data at certain points. This is obviously because we are cutting the domain in a very strange way, or there is an empty void space along the line. That is the zone, the second zone, and the zero drop is where the line is going exactly on the surface. We could visualize pressure to see the full pressure plot. And now, playing with the position of the probe line, we can get and obtain the results of the whole simulation. But now, as the last thing that we would like to do in order to gather most of the data in the most comprehensive way will be to plot the data over time. In order to do that, I will just go back to our transient simulation, apply the results, and load it. We will go, give some opacity to it so that we can see where the probe is positioned. I will add another filter, and now it's a little shortcut. With Control Space, you can start typing the name of the filter, and with Enter decide that, yay, this is the one that I want to see. We'll put the probe in the middle of the domain. Before we apply plot selection over time, we need to select the point data to cell data filter, which will change the point data that is stored in the probe, that is positioned here. It will change the data that is stored inside the probe into cell data that can be visualized on a graph. And after that, when we have the point data to cell data filter applied to the probe, we just go, once more choose the select cells on, select the cell, and then apply the filter, that is the plot selection over time filter. After applying it, we will have this very nice plot of values, for example, velocity and cell and magnitude, which can be saved as a screenshot or saved as a data point. In order to calculate the force that is acting on any kind of surface, there are two ways. First of all, in the online simulation, before you run your simulation, you can add what's called the result control items. And in the surface data items, you can choose to see the area integrals, to see the total force or total pressure force that is acting on particular faces. Or in the other result control item is forces and moments. Also, you can calculate the forces and moments coefficients. This, when applied to particular faces of your simulation, for example, on these particular faces here, or if this was an airfoil or a blade or anything, will give you the moments and forces in the three basic coordinate directions. If, on the other hand, you did not have the forces and moments coefficients result ready at the very beginning, what you can do is load the particular faces of interest. Let's, for the sake of example, we'll use the same ones that we had previously. That is 80. I think these were the ones. We're only interested in the pressure forces because the pressure is the thing that will create the force acting on the blades. All right. Now, in order to get the forces, we need to have the normal direction. So first we'll generate normals, generate surface normals. We'll calculate the cell normals because they are interesting for us. Now, using the calculator, we will multiply the cell data vectors, the normals, times the pressure. This will have the normal force acting on this particular element. And now, if I want to have the total value, I will integrate the variables. If you take a look at the cell data items, the result of the integration, so these results here, will be the integrated force times the face area. So basically the total drag, lift or pitch depending on the direction that you're looking at. In this case, I would say that the Y direction would be the drag, the Z direction would be the lift, and X direction would be the pitch for this simulation. I would like to thank you for participating in this post-processing webinar. Until next time, bye-bye.